Welcome to Talk Tensors. Whether you are prepping for a development meeting, evaluating your company's compute budget, or you're just, insanely curious about where AI is actually heading, you've probably felt the ground shifting over the past few days.
Yeah, you really can't ignore it at this point.
Right. I mean, if you spend any time on X or Hacker News or, frankly, any developer forum, you already know the subject of today's deep dive. The machine learning community is kind of experiencing this collective double take right now.
A double take is, it's definitely the right word for it. It's a massive shift.
It is. We are looking at a paradigm shift that has everyone asking a really uncomfortable question, which is, why are we so obsessed with these trillion parameter behemoths when a meticulously engineered 2.4 billion parameter model is suddenly stepping into the ring and, trading blows with 13 billion parameter giants?
It's really the defining question of this current cycle we're in. We're witnessing a profound pivot in the entire philosophy of machine learning. Because for the last several years, the default, completely unquestioned assumption has been that scale is everything. Right? Scale is the ultimate arbiter of capability. The bigger the model, the better it performs.
Brute force, basically.
Exactly, brute force. But today, we are dissecting a technology that fundamentally shatters that assumption. It proves that optimization and your actual training methodology can outpace raw scale.
So in this deep dive, we are unpacking this viral breakthrough in small language models, or SLMs. We're talking about a newly introduced family of highly optimized 1.2 billion and 2.4 billion parameter models. And to be really specific here, we are talking about non-embedding parameters.
Right, which is an important distinction for the engineers listening.
For sure. And the headline here, the thing that's blowing people's minds, is that these models can run completely locally on just an everyday mobile phone, disconnected from the cloud, yet their benchmark performance rivals, and in some cases completely exceeds, established titans like LLaMA 213B and Mistral 7B.
And, the end result is obviously headline grabbing. A tiny, super potent model. But the true story, the actual reason researchers are obsessing over this, is the methodology used to get there.
Yeah, the how.
Right. They haven't just trained a good model. They've published this radically transparent, highly scalable training strategy that literally rewrites the established scientific laws regarding compute optimal data ratios.
Okay, let's give you the listener the one-sentence thesis of this entire deep dive before we get deep into the weeds. This technology proves that by radically rethinking the learning rate scheduler and breaking the old scaling laws, we can cram exponentially more data into tiny models,
making edge AI deployment both incredibly cheap and incredibly potent.
Exactly. It's a masterclass in challenging conventional wisdom.
Through really rigorous, transparent experimentation.
Okay, let's unpack this. Over the next hour or so, we are going to walk you through the entire life cycle of this breakthrough. We'll examine the ingenious wind tunnel design experiments, the specific architectural decisions like depth and vocabulary, and the real-world performance metrics on everyday hardware.
And most importantly, the broader implications this has for the whole field. We aren't just looking at a new product here. We are looking at a new blueprint for how models, small and large, will probably be trained moving forward.
Yeah, so to truly appreciate the magnitude of this blueprint, we have to start by zooming out, right? We have to look at the pre-existing landscape.
We do, because the significance of a 2.4 billion parameter breakthrough is lost if we don't understand the agonizing limitations of the current industry trajectory.
We have to understand the gap before we understand the bridge. So let's rewind to the discovery of the original scaling laws around 2020. This was heavily publicized by institutions like OpenAI. The prevailing logic essentially stated that if you want a smarter model, you need more parameters, period.
More parameters and exponentially more compute, which kicked off an arms race.
A very expensive arms race.
Incredibly expensive. The industry aggressively pursued large language models, ballooning from tens of billions to hundreds of billions to over 1 trillion parameters. And the logic was sound based on the data they had at the time, but the side effects of that trajectory are just severe.
Because training models of that scale is a monumental undertaking. You're talking about tens of millions of dollars in compute costs alone.
Thousands of cutting-edge GPUs running continuously for months. And beyond the financial cost, there's a massive scientific bottleneck.
Right, because you can't experiment.
Exactly. If it costs $20 million to train a model, you absolutely cannot afford to run trial and error experiments. The empirical understanding of how these massive LLMs actually work under the hood remains surprisingly elusive.
You're forced to rely on intuition.
Intuition, educated guesses, and fragmented scaling laws. You can't just tweak a single hyperparameter and say, hey, let's rerun this 100 billion parameter training loop and see what happens.
Right, the science just becomes too rigid. And then you have the deployment side. Let's say a massive tech company actually successfully trains a trillion parameter model. If I'm a software developer and I want to integrate that intelligence into a local app on a user's laptop or smartphone, I'm completely out of luck.
It's completely impossible to fit it in the device's memory.
Right, so I'm forced to build a pipeline that sends the user's private data to a massive server farm via an API, wait for the giant model to process it, and send it back.
Which introduces latency. It requires a constant internet connection. It fundamentally compromises user data privacy, and it incurs ongoing cloud hosting costs.
It's completely unfeasible for offline edge deployment. And this glaring limitation is exactly what sparked the recent resurgence of small language models in the first place.
We've definitely seen a wave of these sub-7 billion parameter models hitting the scene. Microsoft's Phi series has been hugely popular.
Tiny Llama, Mobile LM, Google's Gemma models.
Right. They prove that there is a massive appetite for intelligence that can live locally on a personal device. But, and this is the crucial part, they also highlighted a persistent capability gap.
Because previous SLMs often struggled to achieve the generalized abilities of their larger counterparts.
Exactly. Many of them achieved high scores on specific academic benchmarks by training heavily on highly curated synthetic textbook data.
They were basically cramming for the tests.
That's a very apt analogy. They were excellent at answering specific types of questions, but when deployed in messy real-world user interactions, their reasoning often degraded quickly.
And the training methodologies for these previous SLMs were often pretty opaque, right?
Very opaque. The community was handed the final model, but not a transparent, predictable scientific methodology for how it was achieved. Getting an SLM to perform well was viewed as a bit of a dark art.
Heavily reliant on undocumented data curation tricks. So that sets the stage perfectly. The technology we are analyzing today targets that exact gap. It provides the robust capabilities of a 13 billion parameter model, but packaged into a tiny footprint.
And more importantly, the researchers didn't treat this SLM as just a final product to be shipped. They treated it as a scientific testing ground.
They used it as a proxy to discover universal laws of model training that the rest of the industry had been too resource-constrained to actually find.
Right, and they introduced this concept they call model wind tunnel experiments. It is a profoundly elegant approach to the economics of machine learning research.
I'm absolutely fascinated by this analogy because think about an aerospace engineering firm. Before they build a massive, multi-million-dollar passenger jet, they would never just sketch the aerodynamics on a whiteboard, build the full-size plane, and hope it flies.
The financial risk would be catastrophic.
Right. Instead, they build a highly precise scale model, they put it in a wind tunnel, and they subject it to rigorous physical testing to understand the universal laws of aerodynamics.
And the researchers behind this AI technology applied that exact same physical engineering principle to language models.
Because a mathematical risk of training a massive LLM is just as catastrophic as a plane crashing.
It really is. If you misconfigure a hyperparameter on a trillion parameter run, you might not find out until you've burned millions of dollars in GPU time, and suddenly the loss function diverges.
So by running tests on what we can call micromodels, specifically sizing them at 0.0009 billion, 0.03 billion, and 0.17 billion parameters, they created a totally risk-free environment.
At those microscopic sizes, they could conduct thousands of full training runs for practically pennies on the dollar.
And they isolated universal training dynamics that actually hold true across all scales, from the micromodels all the way up to the multi-billion parameter deployment models.
So let's look at the specific demons they were trying to exercise in this wind tunnel. The first major hurdle they tackled was hyperparameter stability.
Right, because for anyone who hasn't stared at a PyTorch training loop at 3 a.m., tuning hyperparameters is notoriously frustrating.
It is the bane of many machine learning engineers. You might find a learning rate or an initialization variance that works perfectly for a tiny 100 million parameter test model. But the moment you scale the architecture up to 10 billion parameters,
that same learning rate might cause the gradients to explode.
Exactly. And the model completely fails to learn.
So how did they solve this? How do you ensure that the aerodynamics of the small model apply to the massive jet?
They utilized a strict mathematical framework known as tensor programs, specifically implementing precise width scaling and depth scaling.
Okay, let's translate that for the audience. When we say width and depth scaling, what is actually physically happening to the numbers flowing through the network?
Think of the neural network as a series of interconnected rivers. The width is how wide the river is, the hidden dimension size, and the depth is how many waterfalls or layers the water has to cascade down.
Okay, I track that.
As you build a bigger model, you are adding wider rivers and more waterfalls. If you don't adjust the flow rate, the water eventually overflows the banks. So in tensor programs, they apply specific scaling multipliers to the outputs of different layers.
Basically giving the riverbanks higher walls as the water volume increases.
That's the principle. For example, they multiply the output of the embedding layer by a specific calculated scale factor. For the residual connections, which act as bypass channels for the water volume, they scale the output tensor of a block before adding it back to the main flow.
And that scale factor is derived directly from the total depth of the network.
Yes. They also adjusted the initialization standard deviation.
Meaning the random numbers the model starts with before it actually learns anything.
Right. They set that initial variance inversely proportional to the square root of the hidden dimension, relative to a fixed base dimension. They even scaled the learning rate of individual two-dimensional tensor parameters.
That level of microscopic control over the math seems tedious, but the payoff is massive, isn't it?
The payoff is what we call hyperparameter invariance. Through all of this careful mathematical balancing, they achieved a state where the optimal settings do not wildly shift when you drastically increase the model size.
And they proved this empirically in the wind tunnel. They ran 6 distinct sets of learning rate experiments, testing model sizes ranging from a tiny 0.04 billion up to 0.5 billion parameters.
And even though the physical volume of the model increased more than tenfold across those tests, the optimal base learning rate remained stubbornly, reliably stable at approximately 0.01.
Which is incredible.
It is. And to ensure this wasn't just a fluke, a small scale, they took that 0.01 learning rate and applied it blindly to a 2.1 billion parameter model.
And it worked perfectly. It achieved the lowest loss.
It eliminates the dark art entirely. It removes the need for expensive, sweeping hyperparameter searches every time an organization wants to scale up their architecture. The cost savings alone are astronomical.
But the wind tunnel experiments yielded another massive discovery, and this one has to do with batch size. Finding the perfect batch size, the amount of data you show the model at one time before it updates its weights, is a classic optimization headache.
It really is. Because if you feed it too much data at once, your compute costs skyrocket unnecessarily. If you feed it too little, the model's training drags on forever, and it might struggle to minimize its error rate.
It's a delicate balance of convergence speed versus compute budget.
Exactly. And the researchers wanted to find a mathematical law governing this balance. They ran exhaustive experiments on their micromodels, training each one across 6 different batch sizes while locking in that newly discovered stable 0.01 learning rate.
They meticulously tracked the model's error rate at every single point, plotting the batch sizes against the total number of data tokens consumed. What did the topography of that data actually reveal?
They found a stunningly clear linear relationship when plotted in log space. By connecting the points that achieved the lowest possible loss for the least amount of compute, they derived a predictable, universal formula.
And conceptually, the relationship reveals that the optimal batch size must shift significantly larger as the training loss decreases over time.
Yes. The formula proves that the optimal batch size scales exponentially with the inverse of the loss.
Okay, let's avoid the raw algebra and visualize this. Imagine driving a manual transmission car. When you first start from a dead stop, you're in first gear. You have a lot of torque, but you are moving slowly, looking closely at the road immediately in front of you. That is the beginning of training with a high error rate and a smaller batch size.
That's a perfect parallel. The model is making large adjustments based on immediate, small glimpses of data.
But as you accelerate, as the model starts understanding the broader patterns of language and its error rate drops, you can't stay in first gear. The engine will redline. You have to shift into higher gears.
Right, you start covering more ground, looking further down the highway, taking in a much larger view of the environment.
And shifting into those higher gears is the equivalent of dynamically increasing the batch size.
Precisely. As the loss landscape flattens out and the obvious errors are corrected, the model needs a broader, more comprehensive view of the data set, a massive batch size, to accurately calculate the subtle gradients needed to find the true bottom of the loss curve.
By following this derived law, they could predictably adjust the batch size on the fly, ensuring every single GPU cycle was used with maximum efficiency.
But this level of optimization, as impressive as it is, feels like the warm-up act.
It is time to discuss what is arguably the single most important breakthrough in this entire body of research, the mechanism that actually allows this tiny model to punch so far above its weight class. We need to talk about the learning rate scheduler.
This is the core innovation, the warm-up stable decay, or WSD learning rate scheduler. The wind tunnel experiments laid the foundation, but the WSD scheduler is the engine that actually drives their record-breaking benchmark results.
To understand why WSD is causing such a paradigm shift, we first have to understand the flawed industry standard it is replacing. Because if an engineer is training a language model today, it's almost guaranteed they're using a cosine learning rate scheduler.
The cosine scheduler has been the default choice for years. It operates on a predefined curve. It begins with a brief warm-up period to prevent early instability, reaches a peak learning rate, and then gradually, continuously decreases that rate following the shape of a cosine wave.
All the way down to a minimum value right as the training run concludes.
Exactly.
But the fatal flaw of the cosine scheduler is that it demands clairvoyance. It forces the engineer to predefine the exact number of total training steps before the model even sees its first token of data.
You literally have to dictate the finish line before the race begins. The learning rate is mathematically tied to that total step count. It will hit its minimum value exactly at the final step you defined.
Let's explore why that's such a massive problem in the real world. Imagine you are halfway through a massive multi-month training run. You suddenly get a huge influx of funding, allowing you to buy more compute time. Or maybe your data engineering team just finished cleaning an incredible new dataset of 100 billion tokens.
And you naturally want to keep training the model to make it smarter.
Right. But with a cosine scheduler, you are trapped.
You're completely trapped. If you just try to extend the training, the learning rate has already dropped too low to effectively absorb the new information.
And if you try to guess the new total steps and adjust the curve mid-flight, you disrupt the training dynamics.
Researchers have thoroughly documented that if your predefined step count doesn't perfectly match the actual optimal stopping point, the model's final performance severely suffers. You are locked into the trajectory you chose on day one.
It's incredibly inflexible. So the researchers looked at this and asked, why does the cosine curve work well when we actually do guess the total steps correctly?
And they identified two distinct, mechanically separate benefits bundled together in that curve. First, the cosine scheduler spends a significant portion of its early training time at a relatively high learning rate. This forces the model to broadly explore the global loss landscape.
And second, it features a long, gradual decay at the very end, which allows the model to settle precisely into a deep local optimum.
They took those two distinct benefits, exploration and exploitation, and completely decoupled them. Enter the WSD scheduler.
Let's walk through the three distinct phases, starting with phase one, the warm-up phase.
This phase is standard practice. The learning rate rapidly ascends from 0 to its predetermined maximum. This gently introduces the network to the data without causing the initialized weights to shatter from massive sudden updates.
Makes sense. Once it hits that maximum rate, we enter phase two, which is where things radically diverge from the standard, the stable phase.
Instead of immediately beginning a long, slow decline like the cosine wave, the learning rate is locked in. It stays flat at that maximum optimal rate. For billions, even trillions of tokens, the learning rate does not drop.
So during the stable phase, the model is aggressively exploring. It's bounding across the high-dimensional topography of the data, refusing to settle down, continuously searching for the absolute best generalized understanding of the language distribution.
It's gathering a massive breadth of knowledge. But because the learning rate is so high, it isn't refining that knowledge perfectly. It's painting with a very broad brush.
Which brings us to the third phase. And this is where the magic happens, the decay phase. Instead of a gradual meandering decline spanning the entire training run, the WSD scheduler triggers a sudden, aggressive, exponential drop in the learning rate.
And the effect on the model's architecture is immediate and dramatic. During this rapid decay phase, as the learning rate plummets, the training loss experiences a sudden cliff drop.
The model violently shifts its behavior from broad exploration to razor-sharp exploitation.
It takes all that broadly gathered knowledge and forcefully locks it into a highly optimized, deep local minimum.
I picture it like a skydiver in freefall during the stable phase. They are covering miles of territory, scanning the entire landscape below, remaining high above the ground. Then, the decay phase triggers. They pull the parachute, their speed exponentially drops, and they maneuver to land perfectly on a target the size of a dime.
That analogy perfectly captures the transition. But the true power of the WSD scheduler isn't just the final performance. It's the unprecedented flexibility it grants the engineer.
Which brings us to a massive logistical breakthrough: the 10% rule and intermediate reusability. Let's dive into this. How long does that sudden parachute drop actually need to be?
Through extensive wind tunnel experimentation, they discovered that the decay phase does not need to be long at all. They found that an exponential decay phase requiring only about 10% of the total tokens consumed during the prior stable phase is completely sufficient for the model to fully converge. Yeah. They tested shorter decays, like 2.5%, and the model failed to settle. But at roughly 10%, it consistently reached optimal performance.
Think about the monumental implications this has for a machine learning team. Because the stable phase is just a flat line, you can leave it running indefinitely. It is an open-ended training loop. You do not have to predefine when you will stop.
It completely removes the anxiety of guessing the total training steps. You just let the model devour data.
And whenever you decide you want to test the model's capabilities, or perhaps you finally run out of compute budget, you simply take the current checkpoint from that stable phase, branch it off, run a short 10% decay phase, and you instantly possess a fully converged optimal model.
The modularity is unprecedented. Imagine you are training a foundational model. You can save a stable checkpoint at 40 billion tokens, branch off, run a quick decay, and evaluate its logic skills.
While you let the main stable run continue.
Exactly. At 80 billion tokens, you save another checkpoint, run another quick decay, and evaluate it again. You are building a library of infinitely reusable, optimizable states.
It fundamentally changes the economics of evaluating training progress. But we can't just accept that the loss drops magically during this decay phase, right? For the highly technical audience members who want to understand the actual physics of the neural network, the researchers provided a brilliant analysis of the gradient dynamics. Let's get into the mathematical weeds. What is physically happening to the weights and gradients when that parachute opens?
The researchers wanted empirical proof of the exploration to exploitation shift. So they tracked the maximal weight element updates across all the crucial weight matrices in the network, specifically monitoring components like the gate projection and query projection modules in the attention layers.
What was the behavior during the long, flat, stable phase?
During the stable phase, while the learning rate is high, the model's checkpoints experience massive continuous weight updates. The internal parameters are shifting significantly. Yet, surprisingly, if you track the actual training loss during this period, the reduction is minimal.
So the model is doing a ton of mathematical work, the weights are thrashing around, but it isn't actually getting that much better at predicting the next token.
It's moving incredibly fast, but it's not moving straight downhill. It's traversing the walls of the loss landscape, exploring different valleys without committing to the bottom of any of them.
But then the 10% decay phase initiates.
The moment the decay starts, the overall magnitude of the weight alterations drops significantly, simply because the learning rate multiplier is falling. However, paradoxically, the loss begins to decrease at a drastically accelerated rate.
How does that make physical sense? How can smaller movements in the weights result in a much faster plunge toward the optimal answer?
To explain that paradox, they analyzed the gradient vectors. They discovered that during the decay phase, while the overall norm of the gradient diminishes, the cosine of the angle between consecutive gradients predominantly shifts to positive values.
Let's visualize that vector math. During the stable phase, the model is bouncing back and forth, zigzagging wildly. The angles between its steps are all over the place. But when the decay hits, the cosine turns positive, meaning
the model stops zigzagging, it aligns. The gradients begin pointing consistently in one unified direction. It finds the slope and commits to a straight path downwards.
And they took this analysis even deeper, looking at the topography of the landscape itself by calculating the directional derivatives.
This is where the mathematical proof becomes undeniable. They tracked the first and second order directional derivatives along the path of the gradient. As the decay phase progresses, the first order directional derivative diminishes exponentially, which makes sense. It closely tracks the falling learning rate.
If the loss landscape is a mountain range, the first order derivative is how steep the slope is beneath your feet. It gets less steep as you approach the bottom of the valley.
Exactly. But the crucial finding is the second-order directional derivative. During the decay phase, the magnitude of the second-order derivative actually exhibits a slight but distinct increase.
Sticking with the mountain analogy, the second derivative represents the curvature of the ground. It measures how sharply the valley curves upward into a bowl around you.
And if we look at the interaction between these two metrics, it reveals that the overall curvature of the loss function increases by an entire order of magnitude during the decay phase.
Wow.
The model is sharply, precisely locking into a steep, narrow local optimum.
It snaps into the absolute bottom of a steep canyon. This isn't just theory. It is physical, mathematical proof that the WSD scheduler perfectly isolates the exploration of the stable phase from the exploitation of the decay phase. It's an incredibly elegant feat of engineering.
And this elegant engineering leads directly to the most controversial and impactful finding in the entire paper. Because they had this hyper-efficient WSD scheduler, they were able to run experiments that completely shattered the accepted wisdom regarding scaling laws.
This is where we talk about the compute optimal data to model ratio. Let's frame this debate for the listener. For the last couple of years, the gold standard in the industry has been the chinchilla optimal law, derived from a famous 2022 paper by DeepMind.
The chinchilla paper was a landmark moment. Before chinchilla, companies were building massive models, but starving them of data. The chinchilla law essentially argued that as you increase your compute budget, model size and data size should scale at roughly the same proportional rate.
Specifically, they proposed a compute optimal ratio of roughly 20-to-1. For every single parameter in your model, you should train it on about 20 tokens of data. So a 10 billion parameter model needs roughly 200 billion tokens to be perfectly optimal.
The chinchilla ratio forced the industry to course correct and gather much more data. But it's vital to understand how difficult it is to actually prove a scaling law. The chinchilla experiments themselves were phenomenally expensive.
To map out a curve traditionally, you have to train multiple models of varying sizes on multiple data sets of varying sizes entirely from scratch every single time.
It requires quadratic effort. If a researcher wants to test different model sizes against different data limits, the compute cost scales at OM squared. It is prohibitively expensive for most organizations.
This is where the sheer utility of the WSD scheduler changes the game. Remember, WSD allows a developer to branch off from a stable checkpoint at any arbitrary point in time and run a cheap 10% decay to get a fully converged testable model.
So the developers of this new SLM realized they didn't have to start from scratch. They could cheat the quadratic system.
They executed exactly one main training run for each model size. They let the models run indefinitely in the stable phase. Then they simply pause the training at various intervals, say at 10 billion tokens, then 20 billion, then 60 billion tokens.
And for each of those intermediate checkpoints, they branched off, ran a rapid decay phase, and measured the final optimal loss.
They mapped the scaling laws using linear effort instead of quadratic effort. They completely bypassed the massive compute barrier. They tested 6 distinct model sizes, ranging from 0.04 billion up to 2 billion parameters, evaluated the decayed checkpoints across vast amounts of data, and plotted the resulting curves.
And what those curves revealed fundamentally alters the mathematics of artificial intelligence.
So the chinchilla law stated the optimal ratio was 20-to-1. What did this new linear mapping reveal?
The new compute optimal data to model ratio is not 20-to-1. It is approximately 192-to-1.
192x. That is almost an order of magnitude higher than chinchilla.
It proves that as an organization's computation budget scales, they should emphasize data scaling far more heavily than model scaling. The capacity for a small neural network to absorb and utilize data is vastly deeper than the industry previously assumed.
We can pack an immense density of intelligence into a much smaller parameter footprint.
This single finding completely demystifies why these new 1.2 and 2.4 billion parameter models are routinely beating 13 billion parameter giants on complex benchmarks. They have been saturated with an unprecedented density of data.
The stable phase exposed them to roughly 1 trillion tokens, and the WSD architecture actually allowed them to digest it without hitting a capacity wall.
The researchers provided a fascinating historical cross-check to validate this 192x ratio too. They went back and analyzed the published training loss curves for Meta's LLaMA 2 models.
LLaMA 2 was trained using the old cosine scheduler.
Right. However, the researchers mathematically estimated what LLaMA 2's optimal loss envelope would have been if it had possessed the flexibility of a WSD scheduler.
What did that forensic analysis show?
It showed that the true optimal data-to-model ratio for the LLaMA 2 architecture was likely sitting somewhere between 70 to 100 times, which leans much more heavily toward this new 192x finding than the old 20x chinchilla law.
The old models were still drastically undertrained relative to their parameter capacity.
Right.
The economic implications of this 192x ratio are just staggering. If a company can achieve GPT 3.5 or LLaMA 2 level performance by taking a much smaller model and simply saturating it with exponentially more data, their inference costs, the server costs, to actually let users talk to the model plummet.
It's the economic enabler for ubiquitous edge AI. But shoving 1 trillion tokens into a small model isn't enough on its own. You have to be incredibly strategic about the quality and timing of the data you feed it.
Which leads us directly to their two-stage pre-training strategy and how they completely re-engineered the concept of supervised fine-tuning, or SFT. Let's outline the standard operating procedure for training a chatbot today. It generally happens in 2 massive, distinct buckets. First, you execute pre-training. You shovel terabytes of messy, unlabeled internet data, Reddit posts, Wikipedia, raw HTML into the model.
This teaches the model the fundamental grammatical structure of human language. It learns how to predict the next word, but it doesn't know how to be helpful.
Right. So bucket 2 is SFT. You take that pre-trained model and you feed it highly curated, perfectly formatted question and answer pairs. You teach it to stop acting like an autocomplete engine and start acting like a polite, helpful assistant. And this always happens at the very end of the pipeline.
The researchers identified a massive missed opportunity in that standard pipeline. They hypothesized that because the training loss drops so aggressively and the model locks into its deep architecture during the WSD decay phase, that specific time frame presents a unique, highly sensitive window for learning.
So instead of waiting until the model is completely baked to start teaching it how to be an assistant, they intervened during the baking process.
They took high-quality, complex SFT data things like intricate coding questions, K-12 educational textbooks, LeetCode problem sets, and dense mathematical reasoning data sets.
And they injected them directly into the pre-training data stream, specifically mixing them in only during the decay phase.
It's a brilliant integration. But to prove it actually resulted in a superior model, they had to run ablation studies. They trained 2 identical models through the stable phase. For Model A, they ran the decay phase using only standard, messy pre-training data and then applied the high-quality SFT data afterward in a separate step.
For Model B, they injected the high-quality SFT data directly into the decay phase itself, alongside the pre-training data, and then fine-tuned it further.
A perfect A/B test.
How much better was the integrated approach?
Model B performed significantly better across all major benchmarks by introducing highly structured, ability-oriented data precisely while the learning rate is exponentially dropping and the model is finalizing its deep local minimum. The model structurally specializes.
I love how you phrase that, structural specialization. It isn't just painting a thin veneer of conversational helpfulness over a messy brain at the very end. By introducing the logic and reasoning data during the decay plunge, it weaves those high-level cognitive skills directly into the core foundational weights of the architecture.
The empirical data backs that up. It fosters a much more pronounced loss reduction, specifically in relation to the high-quality data distribution. The underlying mechanics of the model become intrinsically more congruent with complex real-world user scenarios.
And if we're going to talk about the physical mechanics of the model, we need to transition to the actual architectural design decisions. To make a model this small, capable of absorbing 1 trillion tokens of data and complex SFT reasoning, the physical layout of the neural network has to be engineered flawlessly. How do they structure the actual layers of the 1.2 and 2.4 billion parameter variants?
They leaned heavily into a deep and thin network architecture. The 1.2 billion parameter model utilizes a stack of 52 distinct layers, while the larger 2.4 billion parameter model uses 40 layers.
Just to provide some context for the listener, 52 layers is quite deep for an SLM. Microsoft's highly regarded Phi 2 model, which is roughly the same size, only uses 32 layers.
It's a deliberate design choice supported by emerging research. Deep and thin architectures are proving to be highly effective for small parameter budgets. They allow the model to build highly complex hierarchical representations of data as it passes through many layers of transformation, without exploding the total parameter count horizontally.
Which is what happens when you simply make a few layers very wide.
Exactly.
They also employed some specific tricks to shave off parameter weight where it wasn't strictly necessary. For the 1.2 billion variant, they utilized group query attention.
Group query attention is a highly efficient optimization. Standard attention mechanisms require a massive amount of memory to store separate key and value pairs for every single attention head. By grouping heads together to share those pairs, they drastically shrink the parameter footprint and the memory required during inference without suffering a significant penalty to the model's reasoning capabilities.
Let's talk about how the model actually reads text, because the vocabulary size on these models is shockingly massive. The tokenizer for the 2.4 billion model commands a vocabulary of 122,753 distinct tokens.
That is an exceptionally large dictionary for a model of this scale. For comparison, the massive LLaMA 2 models use a vocabulary of only 32,000 tokens.
Every token in the vocabulary requires a dedicated embedding vector, which eats up parameters. Why dedicate so much of your strictly limited parameter budget just to the dictionary?
Because a massive vocabulary drastically increases the compression rate of the input data. When the vocabulary is small, a complex word might have to be broken down into 3 or 4 separate tokens. With a vocabulary of 122,000, the model can represent complex words, full Chinese characters, intricate code snippets, or even emojis with a single token.
It requires fewer bytes of memory to represent the same amount of real-world information.
It makes the model highly proficient and highly efficient when processing diverse languages and formatting. The model processes tasks faster because the sequence lengths are effectively shorter. However, those embeddings are expensive. In the 2.4b model, the embeddings alone account for roughly 0.3 billion parameters.
To mitigate that cost, especially in the tightly constrained 1.2 billion model, they scaled the vocabulary down slightly to 73,440 tokens. And they also employed embedding sharing, correct?
Yes, they tied the input embeddings to the output projection layer. Instead of having 2 massive separate matrices, one to convert words into numbers at the start and one to convert numbers back into words at the end, they forced the network to use the exact same weight matrix for both. It is a crucial space-saving optimization.
Okay, we have covered the deep theory, the mathematical scaling laws, and the architectural schematics. Now it is time to ask the question that every single developer and tech enthusiast listening cares about most. What does this actually look like in the real world? How does all of this theory translate when deployed to a device sitting in your pocket?
This is where the theoretical engineering translates into spectacular practical application. Through a rigorous process called in-tour quantization, they compress the model to a size that almost defies logic.
In-tour quantization essentially means taking the highly precise decimal numbers that represent the model's weights and rounding them off to fit into much smaller 4-bit integers. It usually degrades a model's intelligence. How do they avoid lobotomizing it?
They utilize GPTQ weight calibration. It's a highly sophisticated method that doesn't just blindly round numbers. It analyzes the mathematical error introduced by quantizing a specific weight, and then actively adjusts the surrounding weights to compensate for that error, maintaining the overall mathematical balance of the layer.
The result of that careful GPTQ calibration is that the entire footprint of the highly capable 2.4 billion parameter model shrinks down to a microscopic 2 gigabytes.
2 gigabytes is trivial. You can download that payload over a standard cellular 5G connection in a matter of seconds. It fits comfortably within the RAM constraints of almost any modern mobile device.
Once it is downloaded, it operates completely autonomously. No cloud, no API calls, complete user privacy. They benchmark this on standard consumer-grade hardware using deployment frameworks like LLaMA and LLaMA. Let's look at the speed. On a standard iPhone 15 Pro, how fast is this 2 GB model generating text?
On the iPhone 15 Pro, the 2.4 billion parameter model outputs a blazing 18 tokens per second.
I want to pause on that number. 18 tokens per second is significantly faster than the average human can physically read. The model is generating answers faster than you can consume them, all powered by the battery in your phone.
And it isn't limited to flagship Apple Silicon. They tested it on older Android hardware as well. On a Samsung Galaxy S23, it still achieves a highly respectable generation speed of roughly 6.5 tokens per second.
Now, I have to play devil's advocate here. Generating 18 tokens a second locally is incredible, but does running a neural network at that speed on a phone fry the battery in 10 minutes? Does the phone become too hot to hold?
It is a valid concern for any edge deployment, but the efficiency of the in-tour quantization mitigates much of that thermal load. Because the weights are so small, the memory bandwidth required to move them from RAM to the processor is drastically reduced, which is usually where the extreme heat and battery drain originate. It is highly optimized for burst workloads, like a back-and-forth chat interface.
It's an undeniable engineering achievement, but a fast model that doesn't melt your phone is completely useless if it just confidently hallucinates garbage. So we need to rigorously examine the benchmark domination. How did the researchers evaluate this model, and why should we trust these numbers? Because frankly, cherry-picking evaluation metrics is a rampant epidemic in AI research right now.
Skepticism is entirely warranted. The community has seen too many papers claiming state-of-the-art results using highly customized, bespoke evaluation scripts designed to make their specific model look flawless. To ensure rigorous fairness, the researchers utilized an independent, open-source evaluation framework called UltraEval.
But using an open source framework doesn't solve the underlying problem of how a model is asked to take a test. There is a massive discrepancy between testing via perplexity and testing via direct generation.
That is the crux of the evaluation problem, specifically in multiple choice question and answer tasks. Some frameworks test models by having them calculate the probability, the perplexity of each possible answer choice, A, B, C, or D, and selecting the highest probability. Other frameworks demand that the model directly generate the text of the answer.
And different architectures handle those two methods very differently, right?
Drastically differently. For instance, the widely respected Mistral 7B consistently performs better when evaluated using perplexity metrics, but its scores drop when forced into direct generation. Conversely, the models we're discussing today showed the exact opposite bias. They performed better at direct generation.
If you force both models to take the test using the same method, one of them is inherently handicapped. So how do you level the playing field to get a true comparison of their underlying intelligence?
The researchers took the most transparent, equitable approach possible. For every single model evaluated their own, Mistral, LLaMA, LLaMA, they tested them using both methods. In their final published data, they reported the score from the specific method that yielded the highest result for that specific model.
They gave every single competitor the ultimate benefit of the doubt. They allowed Mistral to put its best foot forward using perplexity while they used direct generation. I deeply respect that level of scientific integrity.
When you evaluate the models on that maximally fair playing field, the data highlights are truly staggering. The 2.4 billion parameter model ranks highest on average across all major SLMs. It matches the mighty Mistral 7B in comprehensive English capabilities.
And it absolutely wildly outperforms Mistral 7B in Chinese language tasks, largely thanks to that massive 122K vocabulary we discussed earlier. Let's look at the hard numbers. On the MMLU benchmark, which tests massive multitask language understanding, the 2.4B model scores a 53.46.
On the HumanEval benchmark, which tests complex coding generation, it hits a 50.0. And on GSM-8K, the standard for mathematical word problems, it achieves a 53.83.
In several of these critical reasoning categories, it's not just outperforming the 7 billion parameter models, it's outperforming the LLaMA 213B model. It's consistently beating an architecture that is more than 5 times its physical size.
It is the ultimate validation of the 192x compute optimal data ratio and the WSD scheduler. But the researchers didn't stop at releasing a phenomenal base model. They released an entire expanding family of models, pushing the SLM architecture into completely new territories. We should examine the 3 major variants.
Let's start with the conversational variant, the DPO model.
DPO stands for Direct Preference Optimization. While the base model is incredibly smart, it acts like a document completer. DPO is the modern process of aligning the model's outputs with actual human conversational preferences, similar in goal to the older RLHF techniques.
Teaching it to be a polite, helpful dialogue partner rather than just a textbook encyclopedia.
Precisely. They applied DPO using the massive ultra-feedback dataset. The results are striking. When evaluated on MTBench, which specifically tests conversational ability and instruction following, the 2.4B DPO variant reached a remarkable score of 7.25.
To put that 7.25 in perspective, that tiny 2.4B model beats the massive LLaMA 270B chat model on MTBench. That's a 70 billion parameter model getting out-conversed by something that fits on a smartwatch.
It highlights how efficiently SLMs can learn syntax and alignment. However, the researchers are honest about a phenomenon known as the alignment tax.
Let's explain the tax. It means you don't get conversational smoothness for free.
Exactly. While the model becomes much better at following chat instructions, they noted that some of the raw academic benchmarks score, the pure logic and math scores from the base model, drop slightly after the DPO process. The model trades a tiny fraction of its raw encyclopedic recall for conversational agility. It's a well-documented trade-off across the entire industry.
The second variant is perhaps the most ambitious from an engineering standpoint. The 128K context window model. The standard context window for most models is around 4,000 tokens. They expanded this SLM's memory to 128,000 tokens.
That is the equivalent of feeding the model an entire dense novel or a massive codebase in a single prompt. Expanding context in a small model is incredibly difficult because the attention mechanisms require vast amounts of memory to track the relationships between 128,000 different words simultaneously.
How did they manage to stretch the memory without the model collapsing under the weight of the context?
They had to make structural adjustments. First, they actually had to decouple those shared input-output embeddings we talked about earlier to accommodate vocabulary parallelism. Then they employed advanced techniques like NTK-aware rope-E scaling.
Let's break down rope-E, rotary position embeddings. Basically, the model needs to know the exact order of the words to understand the sentence. Rope-E encodes that position mathematically, almost like points on a circle. What does NTK-aware mean in this context?
When you suddenly increase the context window, the model has to process positions on that circle it has never seen before. Standard rope-E struggles with this out-of-bounds data. NTK-aware scaling dynamically adjusts the mathematical rotation based on the actual length of the prompt, allowing the model to smoothly interpolate those new, distant positions without losing the high-frequency local details of the sentence.
They combine that elegant math with curriculum learning, gradually feeding it longer and longer documents like books and dense academic papers during a specialized training phase. They also heavily injected synthetic long-form question and answer data.
The synthetic QA data forces the model to actively practice context-aware retrieval. It learns how to hunt for a single needle of information buried deep within a 100,000-word haystack.
The results speak for themselves. On the Infinity Bench evaluations, which are designed specifically to torture test long context, this tiny model outperforms architectures like ChatGLM3's 6B128K. It's 2.5 times smaller, but it reasons over massive documents more effectively.
It completely dispels the myth that massive context windows require massive parameter counts. Finally, we have the third variant, which takes a different approach to scaling. The mixture of experts, or MOE model.
MOE architectures are fascinating. Instead of one giant monolithic brain where every neuron fires for every word, you divide the network into specialized departments, the experts. Our router looks at the incoming word and sends it only to the experts best suited to handle it.
It is the ultimate efficiency play. To build this, the researchers utilized a technique called sparse upcycling. Instead of training a MOE entirely from scratch, they took the fully trained, dense 2.4B checkpoint. They essentially copied the crucial multi-layer perceptron layers, the deep reasoning centers of the network, multiple times to initialize the experts.
So they clone the smart brain and then let the clones specialize in different subjects. This upcycling pushes the total non-embedding parameter count up to 13.6 billion.
But the critical factor is the active parameters. During inference, the router only activates 2 out of the 8 available experts for any given token.
Meaning, the model has the vast knowledge capacity of a 13.6 billion parameter network, but the computational cost of running it is equivalent to a roughly 4 billion parameter model.
They implemented a strict load balancing loss function to ensure the router doesn't get lazy and send every token to the same 2 experts, forcing the network to utilize its full distributed capacity.
And the performance of this 4 billion active parameter MOE.
It is phenomenal. It rivals the performance of LLaMA 234B. It scores a 58.9 on MMLU and a massive 61.56 on the GSNA-K math benchmark. It proves that sparse upcycling combined with MOE architecture is an incredibly potent way to scale capabilities while aggressively suppressing inference costs.
Okay, we spent a lot of time analyzing the triumphs of this architecture, but the core ethos of talk tensors is cutting through the hype. It's easy to look at these benchmark charts and assume SLMs are going to completely replace massive LLMs tomorrow. We need to ask the difficult questions. Where are the blind spots? What are the critical caveats that the viral Twitter threads are conveniently ignoring? Let's provide an honest, unvarnished assessment of the limitations.
The most glaring, unavoidable caveat relates to the WSD learning rate scheduler itself. It is undeniably effective at the 2 billion parameter scale. The researchers have mathematically hypothesized that the laws will hold true at larger scales. However, the WSD scheduler has not yet been fully validated on the 100 billion plus parameter giants.
Until an organization actually spends the money to train a GPT-4 or LLaMA 3 class model using WSD from start to finish, we don't know for absolute certain if the math scales flawlessly. It remains an open, multi-million-dollar question at the bleeding frontier of scale.
That is the scientific reality. Beyond the training methodology, we must address the fundamental capability limits of small architectures. Are there cognitive tasks that an SLM simply cannot perform no matter how much data you feed it?
The data suggests there is a distinct logic bottleneck. If you evaluate these models on Big Bench Hard or BBH, a suite of benchmarks specifically designed to test raw multi-step logical reasoning and complex puzzle-solving SLMs universally struggle compared to massive LLMs.
The 192x ratio proves that encyclopedic knowledge and syntax retrieval can be highly compressed into 2.4 billion parameters via massive data exposure. But raw, unstructured logical reasoning, the ability to hold multiple abstract, conflicting concepts in working memory and deduce a novel solution, still appears to be inherently tethered to raw parameter count.
It can perfectly recite the rules of a complex board game, but if you put it in a novel, complex game state against a grandmaster, it will likely lose where a 70 billion parameter model might find a winning strategy.
Precisely. The depth of reasoning requires physical depth in the network. Finally, we have to critically examine the economics of the compute budget. We have praised how cheap this model is to run on a phone, but the creation of the model is a different story entirely.
Yes, to achieve that optimal 192x data-to-model ratio, the training data required is utterly massive. The researchers trained on over 1 trillion tokens just for the stable phase alone.
Pushing 1 trillion tokens through a 2.4 billion parameter architecture, even with the WSD efficiencies, still demands immense institutional-grade compute. You still require massive GPU clusters running for extended periods to train this foundational baseline from scratch.
This technology profoundly democratizes the deployment of highly capable AI. Anyone with a smartphone can now run a powerful model. But it does not necessarily democratize the creation of foundation models from scratch. That power remains in the hands of organizations that can afford the heavy metal.
It is a vital distinction. It's a monumental breakthrough in operational efficiency, but the initial sorting process still requires an industrial furnace.
Okay, with the sobering reality check complete, let's transition to the segment that allows us to dream a little bit. It is time for our Novel Notions segment.
Always a fascinating exercise in extrapolation.
As a reminder for our listeners, this is the segment where we take the specific, proven technical mechanisms we just spent an hour discussing, and we extrapolate them into outlandish but logically plausible future scenarios. Please note, this segment is strictly for entertainment purposes only. Do not base your startup's business model on what we are about to pitch. Novel notion number 1. I am calling this concept the forever stable community brain.
I'm intrigued by the title. What is the core mechanism driving this premise?
The idea is grounded directly in the unprecedented branching ability of the WSD scheduler. Right now, when developers want an open source model, they go to a repository like Hugging Face and they download a finished, fully decayed static model. What if the open source community completely changed that paradigm? What if they pooled resources to host a single, massive foundational model that is permanently, eternally locked in the WSD stable phase?
Capitalizing on the open-ended exploration phase.
Yeah.
It just runs continuously, constantly absorbing the latest internet data, maintaining a high learning rate.
Exactly. It's a living, breathing, continuously exploring brain. When you, as a developer, want to build a highly specialized model for your specific enterprise, you don't download a finished product. You download the active stable checkpoint from that day.
And then the magic happens locally. You take that stable checkpoint and you execute the 10% exponential decay phase on your own local hardware.
Yes. You run that short, computationally cheap 10% decay phase locally, but you feed it your own highly specific, hyper-private data set. Say you are a massive law firm. You feed it millions of pages of confidential legal rulings. Because of the WSD architecture, you are mathematically guaranteed to get a perfectly converged, mathematically optimal model that has locked its deep local minimum directly around your niche legal syntax.
It completely bypasses the clunky, often unstable process of fine-tuning a pre-decayed model. You are finishing the actual core pre-training directly on your own data.
It becomes a universal, continuously improving starting line for bespoke AI, offering perfect alignment without having to ever pre-train from scratch.
That is a highly plausible, potentially disruptive shift in how open source collaboration could function. It moves the community from sharing static artifacts to sharing dynamic, optimizable states. What do you have for novel notion number 2?
I call this one circadian rhythm edge learning. The core idea here is smartphones that essentially dream and structurally rewire their own brains every single night.
Let me analyze the mechanics. I assume this is grounded in a two-stage pre-training strategy, injecting high-quality data during the decay, combined with the microscopic 2GB N24 footprint.
You nailed the architecture. Imagine this scenario. Your phone holds this highly capable 2.4 billion parameter base SLM entirely in its local memory. It runs lightning fast, parsing your requests with zero latency. Throughout the course of your day, the operating system quietly observes your specific messy data. It monitors your text messaging cadence, the specific jargon in your work emails, the syntax of your quick voice notes.
It's gathering a highly personalized, deeply idiosyncratic data set of your daily life.
Exactly. Then you go to sleep, you plug your phone into the charger. The moment the operating system detects it has full power and is idle, it executes a micro-decay phase.
It treats your personal daily data as the high-quality SFT injection.
Yes. Just like the researchers seamlessly injected the K-12 math textbooks during the decay phase to fundamentally alter the model's logic capabilities, your phone injects your daily text messages into a brief WSD decay cycle. It isn't just adding your messages to a retrieval database, it is structurally mathematically adapting the fundamental neural weights of the network to your unique life context.
Every single morning, you wake up to an artificial intelligence that has literally dreamed about your life, digesting your experiences to perfectly tune its reasoning to your exact voice and needs, all executed entirely locally with absolute cryptographic privacy.
It turns the mobile device from a static tool into a continuous, private, biological-style learning laboratory. And given the mathematical efficiency of the 10% decay rule, a modern smartphone neural engine could easily handle that computation overnight without stressing the hardware. It's the ultimate personalized assistant, and the math in this paper proves it's entirely possible.
It certainly forces you to view the dormant computational power of the smartphone sitting on your desk in a completely different light.
It really does. The implications of this research radiate outward into every corner of the tech industry. Which brings us to our final send-off. We have covered scaling laws, gradient topography, and localized edge deployment. But here is a final provocative thought for you, the listener, to mull over as you go about your day. If the researchers can squeeze the comprehensive capabilities of a massive server farm into a tiny 2 GB file that runs on your phone, simply by optimizing how the learning rate decays and pushing data density to the absolute limit, what happens when the industry applies these exact same 192x data-to-model ratios to the next trillion-parameter giant?
If the underlying WSD math holds at that scale, the theoretical ceiling for artificial intelligence capabilities might be vastly, unrecognizably higher than we ever calculated.
Something profound to think about as the arms race continues. Thank you for joining us on this incredible deep dive. The journey through this architecture has been illuminating. Keep questioning the established assumptions, keep learning the math behind the magic, and we will see you next time on Talk Tensors.